In a previous video, I tested the ATLI EON time-lapse camera using a few different rechargeable lithium battery banks to see how long it would last on those battery banks in power-saving mode. There are a few different complications when you're using a battery bank with another device that has long-term power drain. And in that video, I went over that and showed the results. If you want to watch that video, click the link at the end of this video. However, in this video, we're going to be running that time-lapse camera off of alkaline batteries instead, and we're going to see what happens. Now, in order to do this, there's a few different things we need to kind of cover here real quick and to compare. So this is the Brino TLC 200 Pro that uses 4 AA batteries. That's the Brino TLC 2000 that uses 2 AA batteries. If I use 2 AA batteries in that camera, it will last for up to 40 days maximum on just 2 AA batteries. Now, 2 AA batteries is going to have a power rating of about 8 watt-hours. So a AA battery is 1.5 volts as a listing, but it actually measures usually between 1.6 and 1.7 volts with a multimeter, and they usually hold anywhere from 1500 to 2500 milliamp hours depending on the brand and the type of battery. But just for sake of round numbers, we're going to say that it holds a AA battery holds 25 milliamp hour or 2500 milliamp hour, and that's going to have a total of 4 watt-hours capacity in the battery bank, or I'm sorry, the alkaline battery. A 9-volt battery holds a very similar amount of power in it, except that it's 9 volts. So when you actually measure this with a multimeter, it's about 9.6 volts. These typically will hold around 550 milliamp hour, which when you do the math, it comes out to be about 5.3 watt-hours per 9 volt. So we're going to go ahead and mimic since they're pretty much the same or very close to the same, we're going to go ahead and mimic the power capacity of a 9 volt compared to a AA battery, because for this test it's going to be a lot easier. So we're going to take 2 of these 9 volt batteries and we're going to run them in series. That'll give us 18 volts, the same milliamp hour, but the watt hours is going to be double, so it's going to be about 10.6 watt hours, which is a little more than 2 AA batteries. And we're going to run it to this USB buck converter. This is a 12 volt input, puts out 5 volt 2 amp USB outputs. And you can run this anywhere from 6 to 32 volts input, so this will work for our application. This is a USB meter. This will show me all the information we need during the entire process to see how much power is coming out of the battery and how much power the camera is using. We're also going to take the battery out of the camera so there is no power draw whatsoever, and when the time lapse ends, that'll tell us how long it actually lasted, although this little meter will say the same thing. So we're going to go ahead and get this set up and be underway. All right, I got my real simple setup here. We're just going to be doing a time lapse of the outside. It's the beginning of fall here, so we should be getting some decent leaf color changes, leaf fall, and maybe some snowfall and snow melt if it lasts long enough on these batteries here. So as I've said before, running 2 of these batteries in series, so it's 18 volts out, going to the buck converter, and then converts that to 2 5-volt USB ports at 2 amps each, outputs to the meter, which records every bit of data that we need, and then output to the camera. So these 2 batteries here, as I said, have a little over 10 watt-hours in them when they're combined. The internal battery in this camera, or it's actually removable, but the battery has 7.5 watt-hours total capacity in the battery. So what we should see here, based on the specs of this camera, since this camera only lasts 6 days, even if you're doing 30-minute photo intervals, we should be seeing not less than 12 days using these 2 batteries and at least 30 days. So we're going to go ahead and let this go, and we'll come back and we'll just see what happens. All right, it's the same day here, and I think I overlooked something. In this case, it matters. Before, it really didn't when I use the battery banks. Because of the amount of power that is in the 9-volt batteries total, I didn't think about the LEDs that are lit up on that buck converter. And those LEDs usually are around 20 milliamp power draw, and there's 2 of them on the board there. I don't know exactly what the power draw is of those, but I did some calculations just for round numbers, and that buck converter there, just to run the LEDs, it's going to use all the power up on those batteries in about 3.5 days, according to what I calculated. I'm not sure if that's accurate because I don't know the power draw, but I guess we'll find out. If that's the case, we will do this experiment over again in a different way where we're not consuming power. Although with that meter plugged in, if that's the case, that meter itself is probably drawing a little bit of power just to light up that screen. So we'll have to look at that later on if that becomes a problem. And it turns out that I can actually turn that screen off. I was just messing with it. And I think I'm gonna leave the screen on for this because when I see how much power draw that the camera uses and when it turns off, I'll be able to figure out roughly how much power I'm actually losing through the buck converter and through the meter itself, because the meter can't measure itself and the meter can't measure the LED lights in the buck converter because that's before the measurement. So this way I'll be able to figure out how much I'm actually losing through there just by subtracting after we get the final numbers of the milliamps that the camera drew, and we'll just figure out the rest later. All right, it's been about 36 hours and these batteries are completely drained. And last time I checked that, the camera had hardly pulled any power out of that, not even a half a watt hour. So that means that meter and that buck converter are both pulling a lot of power out of there. So we're gonna figure that out here in a second. All right, so in total, the camera only pulled 75 milliamp hours, but that's at 5 volts. So the actual power draw from it was 0.37 watt hours. So nowhere near the capacity that those batteries had. So we're gonna have to figure out just by deduction how much the meter itself and the buck converter used. All right, the real simple math here is the two 9-volt batteries both contain 10.6 watt hours when you combine them. The camera used 0.37 watt hours total, so that means the buck converter plus the meter used 10.23 watt hours of the batteries. Now that's not gonna be an exact number because that's based off 550 milliamps that each battery contains, but it should be close. I would say, you know, within 1 watt hour at least. All right, my meters are really throwing me for a loop here, so I finally got another multimeter that's actually working the way it's supposed to. So this is now hooked up in series with the battery and this buck converter, and now I can see that the buck converter is pulling 5.33 milliamps. And now we'll see what it pulls when I plug in the actual USB meter. The meter is now plugged into the buck converter, and that is using 13.3-ish milliamps, so it's using a little more power than the buck converter itself. All right, so I'm pretty sure this is the correct math on my cocktail napkin. So the buck converter and the meter combined draw 13.3 milliamps, and that's at 12.6 volts. So that equals 0.167 watts of power, and over 36 hours, that will equal 6 watt hours. All right, I got the camera hooked back up here. Again, there's no battery inside of the camera itself. We're hooked up to this lead acid battery just for testing purposes, minus the 13 milliamps that the buck converter and the meter use. We are using a total of 66 milliamps right now, and that's with the camera in its on mode. I just started the time-lapse session, and a little bit that's going to turn off and go to its power saving mode because it is in forced mandatory power saving. As of right now, it's showing that it's using 120 milliamps. That's not true. That shows that this meter is not exactly accurate. When this drops down to 0, that number right there, that means it's in a standby mode. And this is on 30-minute intervals, so once this goes into its standby mode after a couple minutes, it's going to stay in that low power state, a very low power consumption. And then every 30 minutes, it'll turn back on for about 5 to 10 seconds and then turn back off into its lower power state. We're only going to be looking at it when it's in its low power state and not in its on mode. So in standby mode, we're going to observe how much milliamps it's pulling on this meter here, because the 99% of the time it's going to be using the power while it's in standby and not so much when it kicks on, because it only uses this much power when it's actually on fully. All right, that took quite a bit of time for that camera to go into its power saving mode or its standby mode. You can see there is 0 amp draw at this point. And I've been watching this meter here, and one of the problems is you can see that it's off. This meter is auto turn off, and I don't think there's any way to disable that feature, and my other meter does the same thing. So I have to have it sit on this setting in order for it to power everything. And while it still is powering everything, nothing is displaying on the screen, and the only way to do that is to change this back and forth to turn the display on. If I was to do that, then the camera turns off and back on, and then it goes back out of its power saving mode. So anyways, I've been watching this, and I had about 10 seconds after this finally went into its power saving mode, as you can see it's running at 0 there, to watch what happened on the screen here. It went down to 19 milliamps. So we're gonna do some math here. All right, back to the cocktail napkin here. The camera in its power saving mode is using 5.7 milliamps continuously, and that is 0.071 watts at 12.6 volts. Times 36 hours, that gives you 2.58 watt hours of draw over 36 hours. And if we combine that with the power draw of the buck converter and the meter, as you can see, that uses the vast majority of the power itself, that gives you about 8.58 watt hours in total that it used over a period of 36 hours. Two 9-volt batteries is 10.6 watt hours. So that's actually very close to the total capacity of two 9-volt batteries. Now that's best case scenario. In most cases, batteries for their rating, you're never going to be able to use their full capacity. So this here is telling pretty much the full story here. It's pretty accurate. All right, so here is some other math that also confirms this. So two 9-volt batteries in series is still going to be 550 milliamps. That does not increase. The voltage increases to 18 volts. If you run them in parallel, you're still going to get 9 volts, but you're going to increase the milliamps to 1100 milliamps. Either way, it's the same amount of watt hours per battery. But if you consider the power draw, so in this case they were in series, so 550 milliamps with a power draw of 19 milliamps will give you about 29 hours of runtime, roughly. And I looked back at the footage, and this was running for about 30.5 hours. So it was very, very close, and that tells me that these 9-volt batteries actually had a little more capacity than 550 milliamps. So now we're going to go ahead and do something different. Before we do that, though, I had to make a quick correction here. Because it was actually 30.5 hours, that changes this math here. So we used a total of 7.85 watt hours, not the 8.58. It's roughly the same. It doesn't really matter all that much. But if we look at the total capacity of the two 9-volt batteries at 10.6 watt hours, so we used, I would just say, roughly close to 80% of its total capacity. And that's pretty standard for when it comes to batteries. If you're using 80% of its total capacity, that's pretty good. So that tells me that all this math works out, and the meter that I was using is correct. So now we'll move on. It turns out that I don't have to run any more tests on this where I have this camera plugged in for days on end and waste any more batteries, because I have all the information I need right here. So the ATLI EON camera, it uses 0.071 watts per hour while it's in its power saving mode. And it runs for 6.5 days, as I have tested, and that's what it states on the website as well, which equals 156 hours. And if you do the math, it comes out to be about 11 watt hours that it uses within that time. So this battery could possibly be understated as far as its capacity goes, or this might actually run into a lower power state beyond what I've tested, slightly lower. Over here we have the Brino TLC 2000. This runs off of two AA batteries, which equals 5,000 milliamp hours, roughly. It varies depending on the batteries, but that's a good average. So two batteries equals 7.5 watt hours. Very similar to the watt hours of this lithium polymer battery. So this will actually run for at least 30 days, between 30 and 40 days, depending on the intervals that you use. 30 days equals 720 hours, which means it uses 0.01 watts per hour on average. Obviously, it's going to be using more when you're using the screen on there and when it's actually coming on to take its picture and everything, but that's the average amount. So you can see here 0.01 watts per hour, and this camera uses 0.07 roughly watts per hour. So this uses 7 times less power than this camera does. And that tells me that they might actually be able to possibly do an update to the firmware of this ATLI EON camera to use possibly less power and be more comparable to this camera right here, the Brino TLC 2000. So I hope that information was helpful. It shows here that you can basically just take these numbers here and figure out how long this camera will last on something like a battery bank, although that's not a good idea, as I've shown in the last video. But if you were to hook it up to, say, something like a bank of these AA batteries where they're not rechargeable, you'll be able to figure out how long it will actually last on those now in power saving mode pretty easily. I'm not going to do that for you in this video because the numbers are right here. You can probably figure that out on your own. But that's about it for this video. Thanks for watching.